Good afternoon, everybody. In the subject of fluid mechanics, today we are going to have a session on a topic, the flow through pipes. Now, in this particular topic, we will start up with the different contents of today's topic. We will see what is definition of pipe flow, what is laminar and turbulent flow, however, we have already studied these two types of flows in our previous lectures. Then also we will have a recall session, what is the difference between laminar and turbulent flow, and we will explain these two type of flows with a specific experiment called the Reynolds experiment. Then we will see what is a Reynolds number and what is its significance. Then in the flow of pipes, we have different type of losses, in which we have major and minor losses. We will discuss one by one what are the major losses and a number of minor losses. Then two very important gradient lines, the hydraulic gradient line and energy gradient line, and how pipes can be connected like in series or in parallel. And then one practical application in pipe flow regarding siphon. We will see what is a siphon, what is its application, and where we use this siphon. So, starting with the definition of pipe flow. Before discussing pipe flow, we will see what is a pipe. A pipe is a closed conduit which is used to carry any type of fluid, whether it may be water or gas. As you can see in this diagram also, it is very common to us. We all know what is a pipe. It is a closed conduit. Now, when the pipe is running full and when there is no free surface of liquid, then the flow in a pipe is termed as pipe flow whenever the pipe is full, and in this case the flow is under pressure. Secondly, when the pipe is partially full, means it is not running full, it is partially full, like in the case of serial lines, then the pipe flow is not under pressure, and the pressure inside the pipe is same and it is equal to the atmospheric pressure. So, this is in the case of partially full case. Now, once again discussing regarding the laminar and turbulent flow. The laminar flow is said to be laminar if each particle fluid has a definite path. As you can see in this swan type of water flow, this is a kitchen case in which we have a sink, and having in swan tap, the water is coming out of it, and this particular flow of water, we can say it is a laminar case, a laminar flow, because the fluid has a definite path and the path of one particle is not crossed by the another particle. It is very streamlined. That is why it is also called streamlined or viscous flow. And one or two examples in our day to day life, the flow of blood in our veins and arteries and the groundwater flow, these are good examples of laminar flow. Regarding the turbulent flow, in the previous case, if we introduce a spoon in between, then this particular flow, which you can see here, the zigzag or the indefinite flow, this is the case of turbulent flow. A flow is said to be turbulent if the fluid particles do not have a definite path. As we can see here, the path is definite and the flow is laminar, but as soon as we introduce the spoon in between, the flow becomes turbulent. Now, the path is not definite, and the one particle in a path is crossed by the other particle in this turbulent flow. So, that is why this flow is also called the non-laminar flow, the opposite of laminar flow. Since here the fluid particles are moving in a zigzag path, in a zigzag way. Again, one or two examples, the flow of a river water, it is a good example of turbulent flow. Secondly, the flow of a petrol through a pipeline. We often see in the case of petrol pumps, the flow of petrol. It's once again a good example of turbulent flow. Now we will see the relation between the laminar and turbulent flow, or we will try to understand these two types of flows with the help of a very good experiment, important one, the Reynolds experiment, to demonstrate laminar and turbulent flows. Of course, this Reynolds, it's the name of a well-known scientist, the Osborne Reynolds, demonstrated the existence of laminar and turbulent flow with the help of a very simple experiment. And in this experiment, we are using the apparatus as follows: a water tank at a constant water head. We will simultaneously see the diagram also. So this is a small water tank, and once again this is a large one, a constant head tank, the first apparatus part, then a small tank containing dye. So this is the small tank containing dye. Then we have a glass tube 1.5 meters long and 5 centimeter in the diameter. So this is a glass tube, as you can see here also. From here to here we have a glass tube having a length of 1.5 meters and diameter of 5 centimeters, with the bellmouth entrance at one end and a regulating valve at the other end. As you can see here, we have bellmouth entrance and here we have the regulating valve. So this is all regarding the apparatus part of this Reynolds experiment. Now what actually we do in this Reynolds experiment, regarding the procedure part, the water from the tank was allowed to flow through the glass tube. Now the water will allowed to flow. We are controlling the valve here for this small tank. So the water is allowed to flow this glass tube. What happens then? The regulating valve is used to adjust the velocity of flow. Now here I am talking about this valve. This is used to used to control the velocity of flow. A liquid dye. Now this is important. A liquid dye having the specific gravity equal to the specific gravity of water. It was introduced into the glass tube. As you can see here, from this part, a liquid dye, a filament of dye it's introduced here in the glass tube. Now the following observations were made by the Reynolds while performing this experiment. What are the observations? The first one, when the velocity of the flow was low, with the help of regulating valve, when we are controlling the velocity and the velocity is low, it was low, the dye filament in the glass tube was in the form of a straight line. Just look at this diagram. Now this is the glass tube, the outer two lines, and the dye filament, it is in a straighter path. So this is the dye filament. In the case of laminar flow, it is in the straight line. So the velocity of flow was low, the dye filament in the glass tube was in the form of a straight line. This is important, and this was the case of laminar flow according to the Reynolds. Now what next? Whenever with the help of valve we increase the velocity of flow, when we increase the velocity of flow, the dye filament was no longer a straight line now. Now it's not a straight line, but it became wavy, as you can see here. This is the in-between transitional state where the dye filament has become wavy. It's in the form of wave. That's why it's called wavy filament. And this state is called transitional state according to Reynolds, the second state. Once again, with the help of regulating valve, if we further increase the velocity of the flow, the wavy filament, the diafilament broke up. As you can see here, the diafilament has broken up and it has finally diffused in the water. It is diffused in the water. Here it is in the transitional state, but as soon as we increase the velocity of flow, the filament broke up and finally diffused in the water. So these are the three different stages explained by Reynolds with the help of a very simple apparatus, just to understand, to make us understand what is laminar flow, what is turbulent flow, and what is this in between transitional state in the case of pipe flow. Now there are certain aspects which were discovered on the basis of this Reynolds experiment. What are those aspects? The first one is, for the laminar flow, the loss of pressure head is directly proportional to the velocity. This is the first aspect given by or observed by Reynolds. For the turbulent flow, the loss of the pressure head is directly proportional to the velocity raised to n. So this is the second aspect observed by Reynolds. Now what is this n? It's of course it's a constant having the value varying from 1.7 to 2. Now these were the observations made by the Reynolds with the help of Reynolds experiment. Now some more technical terms which are concerned with the pipe flow. A term called the critical velocity. Now what is this? It is the minimum velocity at which the flow changes from laminar flow to the turbulent flow. The minimum velocity at which the flow changes from laminar flow to the turbulent flow, and the critical velocity is further classified into two types: the lower critical velocity and the upper critical velocity. We have two types of these critical velocities. Now what are those two types? First one, the lower critical velocity, the velocity at which the flow enters from the laminar zone to the transitional zone. We have just seen in the Reynolds experiment, we have three different zones or three different stages. The first one, the laminar one; the second, transitional state; the third one is the turbulent state. So the velocity when the flow enters from first stage to the second stage, the laminar stage to the transitional stage or zones, it is called lower critical velocity. Whereas the velocity at which the flow enters from the second stage to the third stage, that is the transitional stage or the transitional zone to the turbulent zone, then that particular velocity is called upper critical velocity. So these are two different types of critical velocities. Now regarding the distribution of velocity or the velocity profiles, these are very interesting. In the case of laminar and turbulent flow, we have different velocity profiles. Both are different for the laminar one and for the turbulent one. Now moving to the first one, in the laminar flow, the velocity profile is parabolic. Now look at this diagram. The velocity profile in the case of laminar flow, it is parabolic in shape. Secondly, the velocity is 0 at the pipe surface, that is at the pipe walls, and it is maximum at the center. Once again, look at this diagram. The velocity is 0 at the pipe surface or at the pipe wall, and it is maximum at the center. So this is the center line of the pipe. It is maximum here and minimum here. We can say 0 here. This is in the case of laminar flow. Whereas in the case of turbulent flow, we have different profile. One more thing, in the case of laminar flow, the maximum velocity is equal to 1.2 times the mean velocity. There's a relation you have to keep in mind, that the maximum velocity in the case of laminar flow is 1.2 times the mean velocity. Now moving to the turbulent state, the second type of flow, how is the velocity profile? In this case, the velocity is not zero at the pipe surface. Now this is the difference. Here the velocity is zero in laminar case, but here it is not zero, it's not touching this line. So that's why in the case of turbulent flow, it has some value. It's not zero at the pipe surface, but it is maximum at the center. So this is the difference in the velocity profiles of laminar flow and the turbulent flow. Now this was all regarding the demonstration of laminar and turbulent flow, the transitional state by Reynolds experiment, how what are the different aspects from coming out of that Reynolds experiment, and what are the velocity profiles. Now we are repeating one word again and again, the Reynolds. Of course, it's a name of a scientist, but with it's also concerned with a very important number, the Reynolds number. Now what is it? Reynolds number is defined as the ratio of inertia force to the viscous force. We all know what is inertia and what is viscosity, or what is viscous force. So it is just the ratio of inertia force to the viscous force. So it's a dimensionless quantity actually, denoted by the term Re. So E is at the subscript of this R, and it's given by rho Vd upon mu. So what is this rho here? We are already aware of this term. It is the density of the liquid. V is the velocity of the flow. D is the diameter of the pipe through which the water is flowing, or any fluid is flowing. And lastly, this mu is the viscosity of the liquid. So this is the mathematical expression for the Reynolds number. Now is there any relation of this Reynolds number with laminar turbulent flow or any transitional state? Yes, my answer is yes. This Reynolds number is very much concerned with this different type of flow. How? Now this is very helpful or useful in predicting whether the flow through the pipeline is laminar or turbulent. How they are interrelated? When the Reynolds number is less than 2000, we can say that the flow is laminar. When the Reynolds number is greater than 4000, the flow is turbulent. And when this Reynolds number is in between this 2000 and 4000, then the flow is in the transitional state, and it is unpredictable. Unpredictable means it's very difficult to predict whether the flow is laminar or it is turbulent. It is the in-between state, the transitional state. So you have seen what is the significance of Reynolds number. We can very clearly explain whether the flow is laminar, turbulent, or in the transitional state. Now some more technical terms, the wetted parameter. Now what is wetted parameter? The parameter of a pipe which remains in contact with the flowing liquid. Repeating once again, the wetted parameter is the parameter of a pipe which remains in contact with the flowing liquid, and it is denoted by capital P. So if the pipe is circular, then that wetted parameter is given by pi into d. It is pi into d, where d is the diameter of pipe. Very simple expression for a pipe running full. If the pipe is running full, the wetted parameter is given by pi d. One more very important technical term, the hydraulic mean depth. Now it is actually the ratio of the cross-sectional area in which the liquid is flowing to the wetted perimeter. So, it is a ratio of area upon perimeter, also known as hydraulic radius. So, hydraulic mean depth is also sometimes termed as hydraulic radius. It is denoted by small alphabet m. Let's look at the mathematical expression. As I just told you, mathematical hydraulic mean depth is given by area upon wetted perimeter. So, it is A upon P. We all know for the pipe running full, a circular pipe, the value of this area, it is pi by 4 d square, and regarding perimeter, wetted perimeter, it is pi into d. So, just cancelling this d with this d and both these pi's, we will just remain with the expression d upon 4. So, finally, for a pipe running full, the hydraulic mean depth is given by diameter of the pipe upon 4, or it may be 0.25 d, one and the same thing. Now, this was the basics of this pipe flow. Now, we are interested to discuss the losses in pipes, the loss of head in pipes. The loss of head in the pipes, it may be due to various reasons, but we broadly classify the losses in two categories: the major loss of head and the minor losses of head. In major loss of head, we have the only one and the major loss, the loss due to friction, the loss of head due to friction, whereas in the case of minor losses of head, we have a lot of losses due to different reasons. The very first one is the loss of head due to sudden enlargement. Secondly, the loss of head due to sudden contraction. The third one, the loss of head due to obstruction in the pipeline. Now, sometimes there is a loss of head at the entrance of pipe and sometimes at the exit of the pipe. So, these are also the losses, minor losses. And whenever there is a change in the direction or a bend in the pipe, then also we face minor losses. So, as you can see, we have different cases in which we observe losses, but the major loss, the main loss, it is due to this friction, and this we will see in detail also, the major loss of head. This major loss is due to the viscosity and turbulence of liquid. Now, here we have two terms, viscosity and turbulence. We all know what exactly is the viscosity, the property of a fluid by virtue of which it offers resistance to the flow, the viscosity. The turbulence, as we have just seen, the zigzag pattern or the behavior of any fluid. So, this particular loss of head due to the friction occurs mainly due to the viscosity factor and turbulence factor. So, it occurs at an uniform rate along the pipe if the size and quality of the pipe remains constant. Means if the pipe has the same size, it is not varying, and the quality of the pipe also remains same throughout the length, then this loss is also occurring at the uniform rate. In general, we denote this major loss by a symbol HF, F for the friction, H for the head. Now, the frictional resistance in the pipeline, it depends upon various factors. The frictional resistance may change due to velocity of flow, it may change due to area of wetted surface, due to the roughness of surface, or due to the density of the liquid. So, we have various factors which affects the frictional resistance. Look at this diagram. Now, this diagram is well explaining the loss of head due to friction. As we know, we have the parabolic profile in the case of laminar flow. If this v is the velocity of flow in this direction, these arrows are towards the right hand side. So these are showing the velocity of flow in this direction, and we all know the frictional force is always in the reverse direction of this velocity of flow, so it will be in the left direction. So this arrow indicates the frictional force of wall on the liquid or on the fluid. So this diagram clearly explains how this friction force opposes this velocity of flow. But we are interested to calculate the loss of head due to friction. How we can calculate that loss? So we have two different formulas, the Darcy-Weisbach formula and one more formula, the Chezy's one. According to the Darcy-Weisbach formula, the loss of head due to the friction is given by 4FL V square upon 2GD. Now what are these different abbreviations stands for? The first one is the HF, the loss of head due to friction. Then the L, it is the length of the pipe. V, the velocity, mean velocity of flow. D, the diameter of the pipe. And F is the coefficient of friction. And this F, it is a function of Reynolds number. It's concerned with the Reynolds number. And 4F is also called Darcy friction factor. Now in this formula, this 4F is called Darcy friction factor. Now regarding the value of this coefficient of friction, as I just told you, it is concerned with the Reynolds number. So F is equal to 16 upon Reynolds number if the flow is laminar, and F is given by 0.079 upon Reynolds number raised to 1 by 4 if the Reynolds number varies from 2000 to 10 lakhs. So if it is in the turbulent side or in the transitional state. So these are the two different values of F depending upon the Reynolds number. So using this particular formula, we can very easily calculate the loss of head due to friction, the formula called Darcy-Weisbach formula. There is another one, simpler one, the Chezy's formula given by V equal to C under root mi. Now this V is the mean velocity of flow through pipe. C is the Chezy's constant, of course with the name of that scientist, Chezy's. And this Chezy's constant is again given by under root W upon F dash. What is this W? We all know it is the specific weight of the liquid. F dash, once again the frictional resistance per unit area at unit velocity. And regarding this M, just we have studied the hydraulic mean depth, and this I, it is the gradient, hydraulic gradient given by HF upon L. It is given by HF upon L. So if we just put the value of I here, HF upon L, and keeping HF on one hand side, we can very well calculate the value of this HF if we know all other parameters. So this is the second formula to calculate the loss of head due to friction. So this is all regarding the major loss, the loss due to friction part. Now we will see what are the different type of minor losses. The minor losses of head, it may be due to various reasons. The first one, it may be due to the sudden enlargement. The first case, the loss of head due to sudden enlargement. Now the liquid flowing from the pipe of small diameter to the pipe of larger diameter is not able to flow the abrupt change of the boundary. This results in the formation of turbulent eddies and hence losses. Now what does it mean? Look at this diagram. Now here the diameter is less d1. Here the diameter is d2, which is more as compared to d1. So, in this case we can say that there is a loss of head due to sudden enlargement. It may be loss of head due to sudden enlargement, and sudden enlargement means the loss, the pipeline is increasing here, it is enlarging. Now, due to this sudden enlargement,